I'm Stephen Foskett, and we're here in San Francisco for Cloud Field Day. We're visiting companies in the cloud space, and we've got a panel of invited delegates who are writers, speakers, podcasters, bloggers, that sort of thing. We've invited them to come here, presentations, to ask questions, and to represent the audience that is not in the room. If you're interested in learning more about Tech Field Day, go to techfieldday.com, and you can find lots of videos from our events at youtube.com/techfieldday.
Hey everyone, I'm Andrea Luzzardi. I'm the engineering lead for distributed systems at Docker, and today I'm going to talk about orchestration at Docker. So we just saw how Docker can manage containers on a single machine, but what happens when you have more than one machine? What happens when you have 2 machines, 10 machines, 1,000 machines? How do you run those containers? So in the engine, since 1.12, so since June, we have orchestration components built in, so what we call the swarm mode. Swarm allows you to join multiple machines together. They're going to communicate and exchange data, and they allow you to run containers, what we call managed containers. A managed container is managed by the engine. If a machine was to go down, then the container would automatically be rescheduled on a different machine for you. So I'll talk into the details, but the orchestration features provide service discovery, load balancing, security, services scaling, and so on. So the first step.
So is a swarm multiple bare metal servers? Is that possible?
Yeah, it could be bare metal. It could be cloud instances. It's just what we consider like a machine is simply any kind of machine, whether it's a VM, bare metal, that runs Docker engine, and that's it.
Good. Okay.
Yeah. So actually the provisioning, like you take any machine, you install Docker, and you run, on the first machine, you run one command, which is called Docker swarm init, and now you have a cluster 1. You can then go to another machine, connect to it, and then type Docker swarm join, and you give the address of any other machine in the cluster, and suddenly they will start to talk to each other. So the first step in order to have communication between machines is security. Like, how do you guarantee that you're actually allowed to talk to that machine? How do you implement policies? How do you know if you can trust like one of the peers of the cluster? So it's like Docker swarm mode is secure by default. Actually, there's no way to run it insecurely, so it's built on top of TLS. All the communication are encrypted. We use what we call the cryptographic node identity. So every single machine in the cluster has a certificate with a public and private key, and basically the fingerprint of that certificate is the identity of the machine. So it's guaranteed to be immutable and guaranteed to be correct by the certificate. So when you want to join a machine into the swarm, you give it what we call a token. So the token is basically your secret. You give to machines when you do a join. They know that, like other machines know that the machine can be trusted, so they send the certificate and now it's part of the cluster. Swarm also takes care of certificate renewal automatically, so by default, every couple of weeks, the certificates are regenerated to avoid security issues if the certificate are like lost or leaked. So once you form a cluster, now it's secure, machine can talk to each other securely. The problem you have is networking. Like, how can you have multiple containers talking to each other? Like on a single machine, it's quite easy. All the containers are running together, so they can just talk, through localhost. But as soon as you have containers running on different machines, you need a way to make them talk to each other. So in Docker 1.12, we have multi-host networking. So it's pluggable to drivers. Our default driver creates an overlay network, which means that every container gets like a private IP address. It's routable from within any other container. So you can you can just talk to that IP, and whether the other container is running locally on a different machine, it doesn't matter. Docker will do the work and find where the other container is located and just route the packets there. So it's really the building block to be able to do multi-machine.
That was just a recent change because 1.12 Gossip got introduced right before we were using console for.
Correct. So actually, we implemented multi-host networking back in Docker 1.7, which was at DockerCon 2015. Right. But it required a KB store, so such as console, etcd.
Right.
And so in 1.12, it was integrated into swarm mode. And so it doesn't require that. So we made it much easier to use. And so that's why the usage is spreading now compared to before, because the setup was much more painful. So, well, that's pretty much what I just explained, but it's the feature we call routing mesh. So the routing mesh allows a container to talk to another. In this example, we have the machine named worker1. If you want to talk to front end, all you have to do is connect to front end, and automatically we will find that the container is located on worker2 and redirect the traffic in a seamless way. So as a user, you don't have to care where the container is located. We also provide ingress traffic. So at some point, networking traffic has to come to your container from outside the cluster, like your web application has to be reachable from the internet. And in Docker 1.12, we have a routing mesh that allows to publish ports in a cluster. So if you want to run like the CATS application we just saw, you can assign it a port, random one or predefined one. And if you connect to any machine in the cluster, disregarding of whether they have the container running or not, you will actually reach that website. Like that machine knows where the container are located and will just forward the request to the right machine. So as a user, you don't have to care where the containers are located, whether they're healthy or not. That's taken care of behind the scenes by the swarm mode. So I'm going to do a little introduction on topology. I talked about nodes being able to join each other. So actually, nodes have roles, and it's defined by the API. So we have worker nodes that actually execute the payload, and then manager nodes. Manager nodes are responsible to actually handle like the state of the cluster. So those are the ones you talk to. First of all, it's for security reasons. Like you can trust in this schema, you can trust those 3 blue nodes. You don't need to give any trust to the green nodes. Like the green nodes, the worker nodes can only execute payload. They cannot like alter the cluster state. They cannot decide to run a new web service. They can basically just subscribe and get work to execute and then report back, but that's pretty much it. Managers connect to each other and form a quorum. So we have built-in HA. For instance, in this example, we have 3 managers, and so they connect to each other, they do leader election, and basically we have 1 leader that performs all the cluster actions, and then we have 2 standby replicas. They heartbeat each other, they make sure that the leader is still working, and in case of failure, so let's say that the leader fails here, the 2 other followers will notice that and will perform a leader election, and automatically another leader is elected and the connections from the worker is rerouted, which means that you get built-in HA and fault tolerance without doing anything. You just have to join machines together and the system will perform all that for you automatically. That's communication internals. I won't go into the details, but we use a few different technologies. We use Raft for consensus, so that's the same algorithm used by key value stores, such as console or etcd. It's a variation of the algorithm used by Zookeeper to actually have a consistent state in a cluster. We use gRPC and protocol buffers for communication between workers and managers. It's a very efficient version protocol. And finally, we have a gossip network, which is a technology that allows to spread information very fast across many, many machines. So those are details. I'm gonna just skip those. So here's the interesting part. Swarm mode introduces a couple of new concepts. So in Docker, you saw before Docker run and Docker PS, which gives you a list of containers. In Docker 1.12, there are new components. There's Docker service. Service is a higher level component of Docker. So you can create services, update services. A service can be scaled, so it's not necessarily backed by just one container. It can be many containers. So as an example from the CATS application you saw, you would probably create like a service named CATS application with one container, but then you can just run Docker service scale and then bring up 10 more. Services use a reconciliation loop. So when containers are scheduled into machines, if something happens, like the machine fails or the container dies, the reconciliation loop will actually try to honor the contract. So you said that you wanted 10 instances and now there are only 8. So it will respond to that by creating 2 brand new instances. In this example here, we did a Docker service create. We specified that we wanted 3 replicas and we're running 1 image. So you can see that the scheduler, so there's a built-in scheduler, decided to put 1 instance on one engine and 2 instances on another engine. They're interconnected to the overlay network, so they can talk to each other even though they don't run on the same machine. You can create different services and attach them to the same network so they can communicate between each other. Here we have 3 instances of a front end plus a Redis service as a backend. And the front end can simply talk to the Redis even though they're not on the same machine. All it has to do is connect to literally like the name Redis, which will DNS resolve to this IP allocated by Swarm mode. So if one of the machines goes down, so in this example we have 2 containers running on one of the machines. If it goes down, the scheduler takes care of taking the machine out of rotation and then rescheduling the 2 instances on different engines. It will also take care of rerouting the network packets. So one machine went down, we moved 2 containers to different machines, and suddenly we rerouted the networking packets so all the clients can still connect to the same IP. They don't even notice that the machine went down. They only notice that it was not reachable for a few seconds, but then it just resumes working automatically.
So with that,
yeah.
With this process, these containers are all stateless, though.
Yeah, stateless. But then, so actually, that's a good time to bring it up. They're stateless by nature, but they provide volume with volume drivers. And the idea is that we don't want to tie a container to a particular machine. We prefer to have a volume driver that can be mounted to different machines, so that if you have, for instance, a Redis or a MySQL, you can attach it a volume and let it like write into the volume. If the machine is to fail, we recreate a new container on a different machine and reattach that volume dynamically, so it resumes with the same data. We heavily rely on volume drivers. So if you're running on cloud, well, there's cloud drivers for every provider. If you run on bare metal, there are drivers by many different vendors. For instance, EMC has a driver called Rexray for EMC SANs, or you can mount NFS or whatnot.
So the containers are a kind of they're a stateless application server that then talks to a database of some sort, basically. Yeah,
and even the database itself is a container. But the container will attach a volume, like a SAN, NFS, or like a cloud drive.
Persistent storage.
Yeah,
some way.
Yeah, correct.
Yeah.
A way to see that is usually you have one machine on the cloud, and it has like EBS, which is like a block storage hard drive attached to that machine. What we do in this case, rather than having like a single drive that contains the operating system plus all the containers, so we have that drive plus we create Amazon drives for each container where you attach a volume to. So if a container was to fail, we don't need to attach entire storage of the entire machine, but we have that tiny storage that only served for the container that can be moved around. So it's the same technology you're already using. When you run like a MySQL on cloud directly with no containers, MySQL is writing to the local disk of the machine, which is EBS. In our case, we have an EBS drive directly for the container, which can be reattached. So it's basically the same experience you already have, but it's automatically reattached for you. So it's the same performance you get when you use like MySQL on Amazon, like your own MySQL, not like RDS, or your own Redis. Same performance. It's just that, you get one basically hard drive, cloud hard drive per container, if you wish.
I'm also thinking about how it would be deployed inside a data center within say, an enterprise customer who doesn't actually have it running in cloud. I have it running in my data center.
Yeah. So for that, like there are different drivers. There are like, there's for instance NFS, GlossaryFS, or there are actual like, storage vendors such as EMC that sell storage solutions like SANS and NAS and whatnot, and they have a driver for Docker called Rexray. And there are different storage vendors like in the industry that provide their own drivers. So they sell, basically they have their own storage solutions that have been used like in enterprises for quite a long time, and we just integrate with those.
Yeah, all you're doing is adding the driver for whatever particular array or configuration you already have running.
Yeah.
The reason I ask is because I don't care about the application. The application by itself is useless without data.
Yeah,
So
correct.
The data needs to live somewhere, and that's what makes the
Yeah,
application.
it makes sense. It makes sense. So basically, like the short answer would be data. Well, it's not a new problem. It's been like an enterprise problem for a long time, and there are solutions such as storage arrays, SANs, NAS, and we have drivers for those, and that's our solution. So an enterprise would just use whatever they already have in place. There's a driver, or they can create a driver, like it's an open API, and you can have your containers reuse your existing infrastructure in terms of storage. I don't know if that answered your question.
What about network security and those pieces? I mean, you create this overlay network, right? But do I lose visibility there? How would I do application level firewalling? How would I do other things? Is that handled by you, or would that be handled by someone?
Both, actually. So regarding network, there are two parts. There's the control plane and data plane. Control plane is the way we actually configure the networks. So right now we do end-to-end encryption for our control plane. So it's where we configure dynamically the network and so on. We use encryption and curation and so on. For the data plane in 112, we support out-of-the-box IPsec, so we can do end-to-end encryption of the data packets of the containers. It's not enabled by default, so it's a flag to enable. We're actually looking for the next release. We're currently doing like performance testing to see what's exactly the overhead and can we enable that by default. Right now, the only reason it's not enabled by default is the cost, like CPU cost and latency and so on. So that's if you want to have network security handled by Docker. Docker defines security domains as different networks. So a container can be attached to one network or multiple networks on a network. If you have, let's say, your database and you only want particular containers to be able to talk to it, one way to do that would be you create like NetDB, for instance, a network name like that, and use IPsec if you decide to, which is just a flag to give. Then you can attach your DB, your database to that NetDB, and all your services that are supposed to talk to the DB, you attach them to the same network. Other containers that are not supposed to talk to the database won't be able to because they're not attached to the same network. The control plane doesn't even get the network information regarding that DBNet unless it's supposed to. Like if an engine doesn't have any container that's supposed to attach to your database network, then it doesn't get even the encryption key. So it literally cannot attach to it. And that probably works for the 80% use case. Of course, it doesn't work all the time, but if that was to fail, you can, you're in your own container within your own networking space, so you can do your own IP tables rules or whatnot. You're in control of the network interface, so you can implement custom solutions on top of that. So we try always to provide an out-of-the-box 80% solution that works seamlessly for everyone, And then we try to provide, lower level interfaces for those like 10 to 20% use cases, so people can implement their own custom solutions.
We've got plugin architecture for lib network too, so you can swap that out.
Yeah.
So if you want to use Calico and do everything with BGP encrypt on top, you could do that. You've got Twistlock, so Twistlock is someone to look at if you're interested in securing things in the direction that they're doing it. They're a pretty interesting startup, so there's a couple options you have available.
Okay. That's just a question I get a lot. I mean, some of this is very smooth, and then some of that is still very early. So that's usually where these questions come from.
So there are different entry points. Usually, like there's all else is to fail. Like you can always swap the driver. You can even implement your own driver if you want. Like if you have like your own network mode in enterprise, then you can just reuse that and not use any Docker specific things.